morning, good afternoon, good evening, depending where you guys are. Let me see if Bob can...
Let me go ahead and share my screen.
Yeah, you share your screen, start presentation. We can start. We have an hour, so for those of you guys who join on time, we should get started. Okay, let me get, see the video, click on, okay. Request remote control. We've done this for a while now, but it's still every time is a little bit tricky. Okay, whoops. In fact, I lost you. Okay, do I have remote control?
You have remote.
Okay, guys, well, let me see if I can do it. Okay, good. As I said, good morning, good afternoon. Welcome to our webinar today on the 6 most common mistakes made in I.S. EX installations. Before we start, let me give you a little bit introduction about Bob, our speaker today. Bob has over 30 years of experience in the EX world and is a Comp EX instructor, as well as an instructor for the ICEX Comp PC scheme. So both schemes he's an instructor of. He's also an inspector and a member of the US UL STP committee. And, you know, in his very long experience, he has dealt with many installations, many inspections. So he's very qualified to run this webinar today and to answer your question, which eventually you can post. Before we go on, I need to take a few moments to introduce our company, GM International, that is running the webinar, why we do what we do. Here we go. So, GM International. GM International is a safety company. We basically engineer, design, manufacture a complete range of intrinsically safe and certified devices. A safety company, which are used in all automation packages, DCS, CSD, fire and gas, and so on, in many industrial sectors, from oil and gas to petrochemical, food and bev, mining, and so on. We have over 40 years of experience, and we are very proud to have internal manufacturing done 100% in our headquarters near Milan, Italy. Beautiful Italy for you guys. However, we are a global player, so we are present in all the continent. We are trying, because we make safety product, we try to have special care in manufacturing the same. So we use state-of-the-art technology. We have 100% traceability of our product, from the incoming components to the end product coming out of our factory. You know, there's a serial number. From that serial number, we can go back and know the entire history of the product. We do 100% full testing on all production through an automated system. We have a complete automated manufacturing process. We are ROSA REACH compliant. We are compliant to many standards around the globe, and including functional safety. So we are SC3 certified. So our products are C3 certified. Some of them, some are C2, but the manufacturing process, the engineering process, the product carry an SC3 certification, means systematic capability up to C3, which is a mandatory requirement under the new edition to 61511 standard, which is a different topics we can talk at some other time in different webinars. We make safety products, and we try to make good safety products because we care and we want to have a better and safer world around us. These are the products we manufacture: I.S. barrier, safety relays, with and without line monitoring. We have also a line of isolators, non-EX isolator, which are also SEAL certified. Power supply, EX and SEAL certified. We have multiplexing. We also have half multiplexers, which are C3 certified. We have termination board to interface the most common system around the market. And we have surge protector, so SPDs, some loop indicator, and we have a division that runs training and services in the functional safety domain, as well as upcoming, probably now, it was planned for 2020, along with Bob's support. It will go in 2021 to have, you know, due to this COVID, which I hope, you know, we are getting over it. It's not the same all over the world. In the US, still a little bit bigger problem we have here in Europe, but thanks God, things are getting better. So we have this division, services, training in the functional safety as well as EX domain. We are present through different subsidiaries around the globe. We have many distributors. We are about 200 people working in GMI, and we run many courses. As I said, used to run many courses, and we have thousands of installations. These are some of our customers, the main system vendors from ABB to Yokogawa. We operate with the EPC contractor all around the globe. And we supply our product to many OEMs on their skids, compressors, drilling rigs, and so on, as well as being on the AVL of many end users, so many oil and gas companies around the globe. And that is about it for GMI introduction. Before I let Bob talk about our 6 common mistake webinar, let me mention to you that the way you can communicate with us is through the question and answer box. There is a box there. You can use it to post questions during the webinar. We will try to answer them at the end of the webinar, along with the question and answer presentation, which we prepare on the question you send during the registration process. Let me give up remote control. Okay, now you have it, Bob.
All right.
If I disappear, I'm just, take my screen off to answer some of your questions live. Okay, Bob, it's all yours.
All right. Thank you, Paulo. And good morning, good afternoon, good evening, wherever you're located. As Paulo said, it's very early in the morning here in Houston, Texas. So fortunately, no phone calls to disturb me this morning or anything like that. So, and again, as Paulo said, the COVID seems to be getting better here also in the United States. Texas was hit pretty hard in July, but we seem to be going in the right direction. So hopefully the same thing holds true wherever you guys are located around the world. So we'll get through this. So the 6 common mistakes. The first thing that we need to understand are what are the standards, the regulations that we need to follow when we're doing intrinsically safe, either design or installations. So these are just some of the examples of some of the major standards or rules and regulations, the documents that we follow. The one real positive thing that you will see with intrinsic safety is that what you may be familiar with in your part of the world as far as some of the rules and regulations, there is a commonality. Many of the US standards, the Canadian standards, as well as the international standards, are all very similar. So a lot of things that we talk about with regards to I.S., they do apply no matter where you are located in the world. So that's a real positive thing. So some of the standards or regulations to follow with regards to intrinsic safety. In the US, we follow what is called the NFPA 70, which is commonly referred to as the National Electric Code. This gets updated every 3 years. The section that deals specifically with intrinsic safety is in Article 504. There's also a reference in Article 505 on intrinsic safety for the zone concept. We also have inspection standard that was just recently published. This is based upon the IEC 60079-17 inspection standard. So we've now adopted that. In Canada, there's a standard specifically around intrinsically safe equipment, but also they follow the CEC, the Canadian Electric Code, with regards to installation and design. In the international world, there's 3 major IEC standards that we follow, as well as the equivalent EN standard. So the -14 standard is our design for EX installations. That's not just I.S., that deals with all different kinds of EX protection concepts, but there is a fairly healthy section within the -14 standard of the specific do's and don'ts with regards to I.S. The -25 standard is your design of an I.S. system. So that gets into a little bit more detail as far as how do we bring this whole design together. It basically goes a little bit further than some of the details in 14, but 14 talks more about maybe the cabling and certain other installation requirements, where 25 deals with maybe more of the design of the system. And then, of course, the -17 is our inspection of EX installations which there's a whole section dedicated to intrinsic safety. And certainly there are other international standards. You might find API, American Petroleum Institute, recommended practices. There are other IEC standards, such as the 61892 series that deals specifically for mobile and fixed offshore units. So you're going to find intrinsic safety referenced in a lot of other standards and regulations, if you will, out there. But these are the main ones. The real key ones to remember is the Dash 14. That's really the key one that we would really focus our attention on.
So guys.
So Paulo, our first poll question.
And this is another way you can communicate with us, is to answer in this poll. We have some questions for you. See if you've been listening. There is no judgment here, just answer freely. We don't know who's answering. What is the international installation standard recognized for the installation design of I.S. system? So we'll give you a minute or so to answer these questions. You have several choices: NFPA 70, CSA, IC 6007917, -17, -14, or -25. It is a little bit of a tricky question, but there is a most correct answer.
That is correct.
That is correct, which I forgot which one it is though. Although we ran this webinar about a week ago, so I should know, and we've done it more than once, but you know, we get too much in our heads.
You've lived a lot of life in the last week, Paulo, so.
Yeah, and we have done a lot. So let me see. Well, you're still answering. It's about, I see answer coming in, so I'll give a few more moments. As I said, let me take this opportunity to remind you, there's a question and answer box there. You can go in there and type any question you like. Of course, pertaining to the webinar, you know, ask, what's my wife cooking? Because I don't know. Or if Bob is enjoying being at 4 a.m. doing a webinar for us. Because we know the answer. He is enjoying.
I love this.
He does. All right, let me head the poll and see the result. Okay, let me share this result. What is a very, very varied response, Bob?
Yeah. So the most correct answer, but again, this is left open to interpretation, but what I would consider to be the most correct answer would be the Dash 14 standard, the 60079-14, because this is truly the design of the installation, if you will. Again, the Dash 25 standard is a design standard, but it's design of the I.S. system, if you will, but that's not incorrect. And of course, NFPA 70 is an installation standard. And, you know, for those of you who are located overseas, you would say, well, that's an international standard. Well, for me, that's my domestic U.S. standard. So the most correct answer, as far as I would be concerned, would be the Dash 14. And that is the standard. By the way, I would also say this, for any of you who are interested in the EX world, the important standard of all the different IEC standards to look at and to understand, the Dash 14 is really the most valuable for a designer, an engineer, to really spend an awful lot of time. And that's the standard that we basically use primarily when we teach a lot of the courses, either under Compex or the IEC, EX, COPC. A lot of what we teach is based upon the Dash 14 standard.
All right.
Okay, so
let's go on. Might have more questions for you later, so watch out.
Yep. So what is it about intrinsic safety that makes it a little bit different than other EX protection concepts? So what we do talk about within the Dash 14 and the Dash 25, as well as all these the other standards and wiring regulations, is that intrinsic safety is a system concept. So it's not a standalone where we may have, say, for example, an EXE light fitting or an EXD motor or an EX whatever. It is a true system concept. In order to work, in order to be approved, it comprises, if you will, various components. The three major components, if you will, is that we obviously have a field device on the right-hand side. We may have a junction box or a marshalling cabinet where we're making our field connections. We have our cable that is going from our associated apparatus and our control circuit. The associated apparatus is really another term, if you will, for our intrinsically safe barrier. So we really have to take into account the three components, if you will, the field device, the cable, the associated apparatus. The control circuit is something that's given. The junction box is something that would be part of our system. But again, the real key thing is to focus our attention on the barrier, the cable, and the field device. So there are two different types of associated apparatus that you will find in the marketplace. The galvanically isolated product, like what you see on the left-hand side, and a Zener type barrier that you will find on the right-hand side. And it's generally very easy, if you're not familiar with the brands or how they look or what have you, by just opening up a panel or looking at a barrier itself. When you typically see a barrier that will have, say, grounding lugs of some sort, that's almost always going to be a Zener barrier type product, because grounding is a very integral part of the use of a Zener barrier. So if you notice on the left-hand side, you do not see those earth tabs or earth studs or grounding lugs or anything, because a galvanically isolated barrier does not require a dedicated I.S. earth. So it's a simple way of just taking a look at a barrier, and if you're not familiar with it, if you see what you see on the right-hand side, that's typically your first indication that you're looking at a Zener barrier. So let's see if I don't think I've skipped a slide here. No, I haven't. Okay, so how they work. So a galvanic isolator, basically what you have a couple different components associated with a galvanically isolator type barrier. You have your transformer protecting fuse on the upper right-hand side. You have a current limiting resistor on the left-hand side. And those will fail to safe position, meaning that they will open up under a fault condition. You have a safety transformer, and then you also have voltage limiting Zener diodes. And so if we have a fault condition coming in from the right-hand side, we might have a cut cable or maybe a surge or something like that. What we have done, by the use of a safety transformer, we've isolated, if you will, that fault condition to stay within the non-hazardous area. It does not get transmitted into the hazardous area. So that's the function of a galvanically isolated product, if you will. Now, under a fault condition, what happens? Again, we have a voltage source that maybe has a short or something like that. Again, the fault current remains in the non-hazardous location. Notice that our galvanically isolated product does not have that requirement of a safety ground. Now, on our left-hand side, the enclosure in the hazardous location, isolation is not needed, but we also may be grounding that particular product. Okay, so there is a situation where we may be grounding that field device, but we do not have to ground, in effect, our associated apparatus, the galvanically isolated product. Now, how that changes, or what's different, if you will, between the galvanically isolated and a Zener barrier, is that a Zener barrier does not have that safety transformer. So we still have the same types of components, if you will. We have our protecting fuse, we have our current limiting resistor. In this case, we have voltage limiting, Zener diodes. So what happens under a particular fault condition? The Zener diodes will open up over an over voltage situation, and that fault is basically diverted into ground. Now, if obviously the energy becomes too high, the fuse will blow, the resistor can also blow. So at all times, we're basically at this point, again, the fault condition is staying in the non-hazardous area. It is not transferred into the hazardous area. That's the key point. Now, under a fault condition, under a Zener barrier, if in fact we don't have a very good ground, or maybe if we don't have a ground at all, a dedicated I.S. earth, or depending on how it's actually wired up with regards to the ground, we could have a fault condition going to both the safety ground as well as the ground located into the hazardous area. So this is one of the critical things that we need to make sure that we do our due diligence when we're doing our designs, is that we're making sure that that our isolated ground, our safety ground, is separate from our normal ground. The reasoning for this is multiple, but basically the main point is that we don't want to have faults that could be generated in the safe area, create an issue in the hazardous location area. So we want to make sure that we have a good fault ground, safety ground in the safe area. That ground connection, that safety earth, if you will, must have a resistance of 1 ohm or less resistance. So it has to be a very good, clean, resistant earth. Generally speaking, you will find that in many cases they will use conductor sizes of very high, but basically 4 millimeter is more or less the minimum size that we would recommend, and that's referenced within the -14 standard as far as what you might have to achieve 1 ohm or less resistance. But it's not uncommon to have a safety earth larger sizes based upon the distance and the type of cable and all that good stuff.
And we have some question on this later on, which we'll answer. Also, we have another poll, Bob. Let me launch it. Let me see if this is pretty easy. What device can typically be installed in conjunction with an I.S. barrier? In the last webinar we did, some guy asked a question, so I'll make it clear for you guys. B and D, answer E, it says B and D. What that means that you're answering B and D. So transmitter and simple device. And somebody asked me, what does B and D means? And I said, well, you know, it seems obvious to me, but I guess not to everybody. So guys, you know, I.S. is inherently safe because it's a low power,
Protection concept.
Yeah, it is. You're right. I got stuck. Protection concept. So that gives it away, you know. Yeah. So, but let's give it a few moments for you guys to answer. As I said, you know, we're not judging anybody, and in fact, you can also vote anonymously. But you know, it's not a school here. It's just. In fact, we have big issues here going back to school, Bob, in Italy. Crazy issues. School starts next week and government is not ready for it. They don't know what to do. Yeah,
same thing here. Lots of schools are doing both virtual and in school. And I'm fortunate, my kids are grown and working in industry, so I don't have to deal with that. But a lot of friends of mine have some younger ones that are really struggling with all that. So yeah, big struggles. So let me answer. So I guess everybody answered correctly. B and D was the most correct answer, but also transmitter, of course. Nobody answered in EX lighting, which, you know, 110 or 220 cannot be made intrinsically safe. That's correct. Yeah, the correct answer is B and D, but a transmitter or a simple device are both devices that can be and are commonly used for use with intrinsic safety. So yes, absolutely. So you guys are paying attention. That's good. We haven't really covered that, but you guys understand the basics of I.S., which is great. Great. All right. I'll close that and we'll continue on. You close that and let's continue. All right. So what are the key mistakes that we usually see is, first off, no dedicated I.S. earth. Again, for Zener barriers, in order to work properly, they do require a dedicated earth. And as we've seen, and this is true in many installations, that clean earth is attached to the dirty earth, or in many cases, the Zener barrier has no dedicated I.S. earth. So when I do inspections, one of the first things I'm going to look for is to see, is there a dedicated earth and how is it attached to the earth? And is that earth separate from our normal dirty earth, right? And again, the resistance for a clean earth needs to be no more than 1 ohm resistance at the length of that cable. So that is usually the biggest fault that we see with regards to the use of Zener barriers, is the fact that we do not have a dedicated intrinsically safe earth. So how do we achieve this with regards to Zener barriers? Or one of the things that people have a tendency to overlook is that typically barriers are going to be mounted to DIN rail. And a DIN rail is obviously a piece of metal. And of course, part of the fact that how the Zener barrier is actually grounded is through the DIN rail. So if we're going to use DIN rail and we're going to use Zener barriers and we're going to mount it inside of a metallic enclosure, then we need to make sure that that DIN rail is isolated from the enclosure to make sure that we're maintaining that separation between the clean earth and dirty earth. So that's another area that's also kind of an issue, or not kind of an issue, it is an issue, that we want to make sure that if we're using Zener barriers, that we're making sure that that Zener, or excuse me, that DIN rail is actually not grounded to the enclosure itself. So over on your right-hand side, you'll see an example where you have typically on the left-hand side, the safe area wiring coming into the barriers. On the right-hand side, you'll see the outgoing on your intrinsically safe wiring. And down at the bottom, you'll see on the bottom left-hand side, your dirty earth, if you will. And then typically on your I.S, you might find your blue I.S earth, or not blue I.S earth, but you see the earth showing there in blue. And that is, again, separate from your normal dirty earth. Mistake number 2, lack of segregation between I.S and non-I.S circuits. In this particular instance, this is a marshalling cabinet, some sort of junction box where we have probably incoming and outgoing from our associated apparatus going out to our field devices. So in this case, it's clearly marked. We have segregation. There's no exposed conductive parts of the wiring. So when we do an inspection on something like this, we want to make sure that there is no copper showing. And again, it's all properly labeled and marked and all that good stuff. Here's another example where we have the power coming in at the top and we have our outgoing down at the bottom indicated by blue wiring. So everything looks fine at this particular instance. But now all of a sudden we start wiring it up, or we have our technician wired it up, or maybe it's coming out of a panel shop and there's a bunch of looping, right? So remember this is mistake number 2, is that segregation requirement requires a 50 mil or 2-inch between your I.S. and non-I.S. And the reasoning why this is important is that we do not want to have inductive currents that are generated from our power conductors somehow get over to our I.S. circuits and potentially create a fault. So this is why we require this 50 mil segregation between I.S. and non-I.S. It's very important. So as a designer, as an engineer, we could be designing systems that are perfect and fantastic, but once it gets out into the field, if the field technician or the operators that are actually doing the installation are not aware of that, then we run into situations like this. So again, this is a pretty common situation. It's not uncommon to see this. So we definitely feel and realize that this is probably one of those big mistakes that we will find in the field. And even when we're having a panel with just a single barrier, such as this particular one, again, we have a situation where we have I.S. coming out of the blue terminals at the bottom. We have our incoming going in at the top, but notice that we have a lack of segregation between our power cables and our intrinsically safe cables. So we need to make sure that segregation is there. So on your left-hand side, this is very nice and tidy where we have our power cables or non-I.S. cables. I say power cables, they don't necessarily have to be power, but our non-I.S. wiring down at the bottom, we have some nice duct work. And then we have our intrinsically safe terminals, typically indicated by the use of light blue terminals. And they're all nicely up at the top. And then we have ductwork that is showing that these are intrinsically safe circuits. So that looks very nice. On the right-hand side, what we have, we're looking inside of an EXD panel where we have some intrinsically safe barrier outputs. And those are basically looping around. Now, if you notice, and I'm going to see if I can draw on this real quick. And I think I can, yeah. This is a partition right here, right? Between basically what we have over here is a contactor and our intrinsically safe barriers over here. So this 50 mil segregation can be in free air, or we can actually have partitions, if you will. And this distance from here to here, from here to here, meets that 50 mil requirement. However, what we have is that we have a power cable over here, we have some I.S. cables over here. We've now defeated that 50 mil segregation between our I.S. and non-I.S. Again, when it came out of the factory, when it was built, it was fine, but then once it was installed by the technician, now all of a sudden we've run into problems with that 50 mil segregation. Now this panel in particular, since this was an EXD panel, if you notice, these are actually compound barrier glands or liquid pore type barrier glands. And unfortunately, they had to tear these all apart and rewire this in order to meet that segregation requirement. So
an expensive mistake.
That's a big issue.
Big, expensive mistake, Bob, huh?
Very big, very expensive. This was one I found for a customer that asked me to come in and do an inspection. And when I shared with them this information, they were not happy. So unfortunately.
let me ask you a question, which I believe somebody asked before, but you know, the partition you just draw on there, that
right.
it has to be isolated material, or can it be metal partition?
So yeah, that's a good question. Typically, typically it's going to be some sort of isolating material. Now, it can be a metal partition. And in reality, the isolation or the segregation requirement can be met in a couple different ways. It can be met, as I mentioned, by free air. It can be met by either a metallic or non-metallic type partition. But we can also meet it by shielding or putting armor on the cables. So there are different ways to achieve this. Excuse me. But yes, partitions can be typically non-metallic or metallic.
I believe it's metallic, but probably needs a grounding connection, right?
That is correct. You would want to make sure that it's grounded. That is correct.
All right, great. So this is mistake number 2.
Mistake number 2. And again, here's a good example. Yeah. And again, yeah, not good. So we just have a lot of.
It looks nice from the outside of the box. You got, you know, blue cable on the right side, gray cable on the right. It looks nice outside.
Yeah, unfortunately with I.S., typically, you know, when we look at it from the outside, it looks very nice. And that's when we get into a detailed inspection, meaning that we open up the panels and we start looking at the internals. That's usually a lot of times when we see the faults. So a lot of intrinsic safety faults you typically will not identify under a visual or close inspection. Sometimes you will, but usually it's the detailed inspection that when we start opening up enclosures, that we start looking and seeing how grounding is done or how the wiring is done. And this is typically where we're going to find a lot of the faults.
Okay, so guys, we have another poll for you, another question. It's easy, but, and Bob mentioned it during the webinars. I was listening, so I know he did. What is the minimum distance requirement between I.S. and non-I.S., which we said you can meet in different ways, through partition, through air, cable glands, and there's different way, but what is this distance? It's a number. It can be 25, 40, 50, or 80 millimeters. The standard talks about millimeters. Probably, I don't know if he mentioned inches, but anyhow, the number is very known in the industry.
So what you will find within the National Electric Code, the NFPA, we do reference both inches and millimeters. So we
it's not an exact translation, right?
No, it's not. It's not exact. So 1 inch is 25.4 millimeters. So to give you an indication what it says within the National Electric Code, and I guess we can give it away now.
Yeah.
The NEC actually says is 2 inches.
2 inches, which is a little more than 50 mm. So safer side. Yeah, 50 mm is what the right answer. Most of you guys, 82% answer correctly. 80 millimeter is better than 50. 40 is not sufficient, right?
That's right. So there are some specific details also with regards to separation between I.S. and I.S. There's actually a 6 mil requirement. So every I.S. terminal or connection point should be at least 6 millimeter. we also don't want to, we also want to make sure that we're not running IS and non-IS within the same cable. But basically then also we have IS to ground must be 3 millimeter. So that's those numbers are pretty much indicative of almost every world standard. So anywhere you go in the world, if you remember 50 mil, 6 mil, 3 mil, you're going to be good.
All right. Let's go on to our mistakes. Well, we have the mistake number 2 still. Okay. Well, this is a good, this is what it should be like.
That's right. This is what we should look for, right? And so we do see that we have, in this case, we actually have our little partition that's located right there. So we have our IS over here and non-IS here. And again, that 50 mil separation has to be from the IS glands to the non-IS glands and all that good stuff. So our wiring should be coming out from our IS over here, and our non-IS should be coming out over here. So again, that's nice, and that's the way we want to see it. Now, let's see, close this, move to this. This is an extreme measure where we're actually taking 2 separate enclosures or series of enclosures and running IS in one and non-IS in another. You don't have to do this, but this is certainly what some people will actually do. Our third mistake is no identification on the enclosures that are actually containing IS circuits. So it is a requirement that, and this is true anywhere in the world that you go, no matter what standard you follow, is that if we have enclosures that contain IS circuits, it shall be labeled definitively, telling the owner, operator, the technician that intrinsically safe circuits are contained inside. So on the left-hand side, we see an exploded view of a junction box. It looks like we have some blue IS terminals on the inside there, but there is no IS label on the enclosure or something that's telling us that it actually contains IS circuits. On the right-hand side, that enclosure does show a label. And typically these labels will be light blue with some sort of verbiage that says contains intrinsically safe circuits. There are different verbiage requirements around the world, but more or less something that states something that says this box or this enclosure contains intrinsically safe circuits is perfectly sufficient to meet that requirement. So when we find this fault, it's an easy fix. We basically say, hey, you need to put a label on it to tell everybody that this is containing intrinsically safe circuits.
And that brings us to our next poll. It's an easy question, but it can be misleading. So guys, before you answer, think it, read it over. True or false? All intrinsically safe cable must be light blue. The first answer were correct. There are some now mixed answers. So either one or the other. You cannot select both. So it's either true or false. Now we're coming close to 50-50. I see the poll coming live here. And so about 50% of you are wrong and 50% are right. There's no other way. We have this. Okay, I think most of you have answered. Let's, I think the right answer has won. Share result. False. False was the correct answer, right, Bob?
Yes, yeah, that is correct. Now, that being said, right, what the standard actually does say, and this is true for almost every standard in the world, it's pretty much a uniform thing, is that the standards, the rules and regulations, the wiring regulations all state something to the effect of, if you're going to use color coding as a means to identify IS, the color shall be light blue. However, that's different from saying that all IS circuits must be light blue. It doesn't say that. It basically says if you're going to use a color coding, then it must be light blue, right? So there is a slight difference. So in reality, a lot of people are under the perception that I always must use light blue cabling for IS. You actually do not, unless, now that being said, there are some clients, some customers around the world that will say, I don't care what the standard says, you must use light blue wiring. That's fine. But what the standards will actually allow you to do is that if you want to use a different coloring, that's okay, but you do need to indicate that that circuit is in effect light blue. So we want to make sure that everybody understands that.
Stop sharing. Okay, here we go. So guys, we can move on. Next mistakes, I guess. Right. Which is marking.
So this leads into, right, no identification used for our intrinsically safe wiring. So again, the standard does say if a color coding is to be used, light blue shall be used for I.S. circuits. But again, all of the standards do allow you some options in using non-blue jacketed cables. So down on your left-hand side, you could actually have some sort of indication on the cable that says intrinsically safe wiring, or if we're using conduit, we have to have some sort of marking on the conduit that is telling us that this conduit is containing intrinsically safe wiring. What we see on the right-hand side is just some instrumentation cable that is not marked at all. So that's not allowed. We have to mark the cable in some way, shape, or form to indicate that these circuits do contain intrinsically safe wiring. Now, one of the important things, and this really isn't one of the mistakes here that we talk about, but it is a mistake, is that we cannot combine I.S. and non-I.S. within the same cable. So if we look at that instrumentation cable on the left-hand side, the middle one down, where we see it looks like 4 pairs, we can't have 2 of those pairs containing I.S. circuits and the other 2 non-I.S. circuits. They either all have to be I.S. or none of them are I.S. Okay, that's an important thing to remember as well. Mistake number 5, and this isn't just an I.S. issue, but this is really an EX issue in general, but selecting the appropriate gland or incorrectly installing the cable glands. So what you see down at the bottom there, you see actually a combination of both putty and liquid core compound glands, which is definitely a no-no. What you see on the right-hand side at the top there, you see a cable gland that's missing its grounding ring, but it's actually attached over the jacket. And the bottom one is where we have the armor is more or less torn away from the retaining ring on that particular gland. So we want to make sure that the glands are installed properly. We also want to make sure that we're using the appropriate glands for the application. So there are different requirements depending on where you are in the world with regards to the types of glands to use. But generally speaking, in the international community, there is not, generally speaking, intrinsically safe glands. There are glands that are blue, but typically what we would do is use what is called an EXE, increased safety type gland, like what you see on the left-hand side, if that's going into a box that's containing I.S. circuits. However, on the other hand, if we have a box that's containing I.S. circuits that's a flame-proof box, we would want to use a flame-proof gland. So we want to make sure that the gland matches up to the protection concept of the enclosure. So down on your left-hand side, you see those little plastic blue glands. Those are perfectly acceptable. Again, those are typically used for I.S. cables, but we do not require the use of blue cable glands. Again, it's more of a convenience, and it's giving us a visual indication that that is containing I.S., but again, it's not typically a requirement. The other things that we don't want to see when we're doing inspections, and again, this is for I.S. or non-I.S., but we don't want to see things like Teflon tape on our glands. We also want to make sure that all of the traveling plugs, like what you see on the right-hand side, those little red plugs, those need to be removed, and in place, a certified plug should be installed into our field devices. So it's kind of an all-encompassing, proper glanding, making sure that the glands are properly installed, and making sure that all of the things like traveling plugs are removed. Those are all key considerations. And then finally, mistake number 6, and this is a big one. We see this more often than not, is what is called a missing descriptive system document, or DSD. So it is a requirement pretty much everywhere in the world when we're doing intrinsic safety, is that we require to have a DSD. So what is a DSD? So what it contains is our loop calculations. It will tell us the approved components for use on the circuit. It should tell us the wiring installation information. the cable lengths and or types, any identification numbers. There should also be a date and the name of the individual, of the designer that designed this system. And if we're using any surge protective devices and analysis. And the important reason why we need this is that as an inspector, when we come in, we want to make sure that what is actually installed matches our DSD. So it's kind of like a roadmap. If we don't have a roadmap, we don't know where we're going. So we need to have that DSD to tell us all this information, to make sure, to validate and verify, to make sure that our intrinsically safe loop is in fact safe. Remember, I told you very early on, this is a system concept. So we're combining our associated apparatus with the cable and our field device and our output from our control circuit. That information is all located on our DSD. So just to give you an example of how to create your DSD, this is the information that we would typically need to have from our field device. So this is the parameters that we will find from the manufacturer, and it'll typically be within their installation documents. So we have this information from this beacon. We take, and then we also look at the inductance and capacitance of the cable that we're using. So typically we can find this from the cable manufacturer. If in fact we cannot find this, there are some default parameters from the -14 standard. So it gives us some default parameters that we can use if we cannot determine this from the actual manufacturer. And then we need to take our output parameters from our device, and depending on the gas group, that will give us the parameters for the particular device that we're looking at. So then, we take all that information, we can plug that into a spreadsheet, and in this case, we plug in the information that's in yellow. Down on the right-hand side, that green information is telling us, hey, this is okay. The input and output parameters are fine, they match. But the important thing that we also see here, and what we see circled, is that number 179. That is telling us, based upon the gas group 2C, this is a hydrogen or acetylene type application, that the maximum cable that we can run is 179 meters. So when we're doing an inspection, we want to make sure, how far is that field device away from our associated apparatus? Is it within that 179 meter range? If it is, we're A-OK. If we're above and beyond that, that means that the total inductance and capacitance has exceeded the safety parameters, and we now have an issue. So that's why our DSDs are so important, to make sure that we have those and that they're generated, and that people are actually producing them for the owner operators. Or if we're an owner operator, we should expect that to come in from any of our sub-suppliers that are building skid packages. So here's just a simple example of our DSD. So I put this together. This is just a real simple block diagram, but more or less, there's our device on the right-hand side with our output parameters. It gives us the information on the cable. It gives us an original reference number, and then it gives us also the information on our device that we're actually taking and protecting in the field, and it also tells us our area classification of what we've actually got this located into. So that's the type of information that we need to generate a DSD. The 60079-25 standard will give you some very good examples of DSDs and how to create a DSD and what actually needs to be on there. But basically, these 3 or 4 slides is more or less the relevant information that you need to know.
All right, Bob.
So we have,
okay, here's our contact details. Very good. Thank you again, Bob. You know, you're always very thorough and clear. You guys, we have about 10 minutes. We go through a small presentation we prepare on your questions, which you pose during the registration process. You can also pose live questions. We can try to answer them. So Bob, I ask you to stop sharing, and I will share my presentation, or the question and answer presentation.
right.
Let me see if I can manage that.
While you're doing that, Paulo, there was a question that came in. Curious about the 100. Yeah, curious on the 179 meters. How did you carry out verification work to verify 179 meter cable? Did the inspector really need to measure each of the I.S. cables? Generally speaking, and that's a great question, most of the time you are way below. Now, again, that was a very extreme example because that was also a 2C gas environment. If it had been a 2B or a 2A gas environment, that length of cable would have actually been significantly longer. But yes, you actually would need to go out and validate to determine. So it may be a very simple situation where you're looking at your control panel and you're measuring and looking off in the distance and you say, okay, that's about 50 meters. Okay, we're fine. But if we're right there, then yes, we actually would have to go right out and validate whether or not it was 179 or 180, right? So generally speaking, it's not a major issue, but it's something that does get overlooked, and we don't want people to overlook that.
Yeah, well, the other question is how capacitor and inductance affect the I.S. loop. They do, because they are storing energy. So the cable, the more capacitance and more inductance, the more energy stored in there. So that's why the cable length matters. Of course, if 179 meters, you are more than 179 meters, there's only one choice. You either bring it closer or you change the cable, because there are better cable in the market, maybe bigger cable, more isolated cable. They offer lower capacitance and inductance per meter. Okay, let's see if we go on to our, you can continue ask questions, no problem. In the meantime, we run our small presentation here. Let me see if I can manage to control it. Okay, first question we got online. What is the difference between safety ground, ground for safety barrier, signal ground, connection point to the shields? Can all of those be connected together, or they need separate ground point? So you covered this, Bob, during the presentation. The ISB, so the intrinsic safety barrier ground, needs to be separate, but let me see the answer we prepared. Actually, you prepared. So, I think this the right answer, the right slide?
Yeah, I think so. I think we had, continue on. I think it shows a drawing.
Yeah, we got this mistake before. Okay.
Yeah, we didn't correct it.
90-minute slide you prepared, Bob. You can trick me into this one. I'm not sure whether this is the end of it or if I click again.
No, I think that's it. That's it. So basically, the question was more on the screens and how we deal with all the various earths, right? Because we talk about dirty earth and clean earth. So I think one of the questions was that came in, how do we deal with the screen wires, in particular, the screening? So generally speaking, what you will find is that that screen wire is connected, it's left floating, unless there's a terminal that we can land at, a spare terminal. But generally what we would do is take that screen and we would tie it off, we'd shrink wrap it or cap it, and we would leave that floating, and then we tie that screen wire back into our clean earth all the way back into the safe area. Again, the separation between dirty earth and clean earth, at some point in time we get to earth, right? So we just want to make sure that we don't have any undue noise and harmonics or anything that can come back through the dirty earth into our I.S. earth. I think the question was too, with regards to non-intrinsically safe control circuits earth, those are typically going to be tied into our dirty earth, if you will. We want to keep that separate from our I.S. earth. So the only thing that we want to connect to our I.S. earth are the screens and the earthing cable, if you will, that's going from your Zener barriers and all the associated apparatus down to the clean earth.
It's important to remember here that the screens, one side needs to be floating, because otherwise you create a path between, safe area and non-safe area, hazardous location. So one of the two hands needs to be floated. Typically, they are grounded in the control room side, but.
Right. And the reason why we do it, why we leave them floating in the hazardous area, is that if there is any inductive currents that get into the screen, then they're all going to be taken back into the safe areas. So it's a more safe installation.
Yeah. Okay, let's go to the next question. If a component of a system is I.S., can the system be considered I.S.? If not, how to ensure the same, or how do I calculate an I.S. circuit? You discussed this in DSD mistake a little bit, but maybe you want to go over this a little more.
Yeah, the important thing to note is when we're doing intrinsic safety, there's more or less, there's two different devices, our field devices. We can do simple devices, and then we also have field devices that actually require certification. So simple devices are things like RTDs, resistors, thermocouple. They do not require certification. So if we want to use a thermocouple in a hazardous location and connect that to an intrinsically safe barrier, generally speaking, they do not require a certification for EX. They can just be used as a general purpose unit, can be used in a hazardous location. However, when we have things like transmitters that store energy, or proximity or solenoid valves or things like that can again be energy storing devices, and there's the parameters that those devices actually do need to be certified, and they will be certified, and they can be certified either as EXD, and in many cases you'll see a lot of transmitters that'll be flame proof, but they can also be certified EXI, and they need to be installed and certified EXI to be used with intrinsic safety.
Yeah, basically, you know, you need to match the barrier with the field transmitter using and the cabling through this entity parameter check, what you describe, the result of a DSD. We as GMI, oops, I went one slide too fast. Are you moving my slides, Bob?
I'm my hands are right here.
I don't know, double clicking. So basically, you know, we have a online tool that allows you to do this check for, of course, GMI barriers, where you enter automatically the parameter of the GMI barrier automatically entered, and you enter the parameters of your device, field device, whether it's an intrinsically safe device, such as a transmitter, or a simple device, like a quant, which will not have any parameters. Then you only enter those of the cable, and we will give you a check. We are coming close to an hour. Let's see if we can answer a few more questions before you guys are let go. What are the pros and cons difference and maintaining issues of Zener versus Galvanic Isolator barrier? We had a specific webinar on this. We run it 3 times, but we can summarize it very briefly.
Yeah, I think the one that's highlighted there is the Zener barriers require the dedicated earth where the galvanic lead doesn't. That's really the biggest issue.
And as you discuss in your, verification in the plant, you know, finding a good earth, less than 1 ohm, dedicated isolator, not easy.
Right.
Okay, let's go. There was a question on live that I typed in. We have a next webinar coming up, or which will discuss all the marking, because it was about marking. We cannot go into the details of the marking now because it will take too long. Can an EXD enclosure have a removable gland plate? If a gland plate is removed for maintenance and reinstalled, does it need to be re-inspected formally?
Correct.
Well, this is the answer you prepare, Bob.
Yeah. So gland plates are typically they're typically thin metal plates used on EXE enclosures, and they are attached via bolts, and they're typically gasketed to maintain a high IP rating. But EXD enclosures are cast, and they must contain a flame-proof, or they must contain an internal explosion. So you will not find, I'm not aware of any flame-proof product that actually has a removable gland plate. And I don't think you would find one out in the marketplace. When you actually
remove a gland,
you can remove a gland, absolutely, but gland plates are really more convenience to put entries into EXE enclosures. You know, the whole idea behind a gland plate is it's a lot easier to machine a gland plate, if you will, than it is a full enclosure. And certainly if you make a mistake with a gland plate, you can replace the gland plate as opposed to having to replace the entire enclosure.
But once you do remove a gland on an EXD enclosure, you need to re-inspect it, right? Or
yeah. So your inspection requirements for EX equipment is an interval no longer than every 3 years. So every 3 years, you must go out and inspect your EX equipment. If you're replacing, say, something and you need to reinstall an EXD gland, well, it should be done by a competent technician, and it should be inspected just as if it was a new installation.
Well, I guess you answered my next question, which is after initial commissioning of an I.S. system, what is the recommended periodicity to validate the system, and what kind of procedure are in place to allow this check without shutting down the process? As you just mentioned, 60079-17 standard mandates 3 years of inspection. Every 3 years, you must re-inspect equipment, right?
Yeah, and here's the thing, with regards to I.S. systems, if it's really undisturbed, right? If we've done an installation, we have our DSD, everything is out there. That doesn't necessarily mean that we have to go in and do a loop check every 3 years. It does not necessarily mean that. What it does mean that it shall be inspected. So here's where this would get, this is more of an interpretation. If I am going to do an inspection on an I.S. installation and it's been out there for 3 years, I'm going to look and I want to see, does all the components match? Yes. Has anything been changed on this? No. If everything looks good from a corrosion resistant standpoint, if there's no undue corrosion, if it hasn't been modified, am I going to actually go in there and do a loop check on everything? No, I'm going to sign off on that because it's basically, if it hadn't been changed, if you will, and it's still in good condition, then I'm probably not going to go and do that full loop check verification.
Yeah.
I'm going to go in and do a visual and close inspection. And again, if everything is fine. Now, if I've changed some components, if I've changed this, I've done something, anything's different, then yes, I might want to do something.
And remember that an I.S. system is intrinsically safe, inherently intrinsically safe, so inherently safe, which means you can do light maintenance on it. You can send a hard command or, whatever you want to do with it, you can do it live. Okay, let's see if we are about an hour, but let's see if a few more questions. You guys stay with us. We have a few more minutes. There was another question that came through registration. How can we address the voltage drop issue when activating a solenoid valve via an I.S. barrier? This is a very typical problem. It has to do with the resistance, which is in a barrier in itself. What it looks to your loop is basically a resistor, which is used to limit the current and is a mandated component for an EXIA certification. So, and it depends on it, the 420 milliamp loop, it can be 300-400 ohms. So It's quite a voltage drop, it's 7, 8, 9, 10 volts. Sometimes you drop across the barrier. This creates a problem when you go into, the question was specific to a DO, but also an AO can have the same problem. You have a transmitter in the field, and it operates fine up to 15, 16, 17 milliamp, and then it just, boom, you cannot reach 20 milliamp because there's not enough power. Well, the answer here, if you allow me, Bob, is to use an isolated barrier, because an isolated barrier, it's a power supply, and it guarantees the voltage that is stated on it. So 17 volt at 20 milliamp, for example, you get 17 volt, period, regardless of the resistor, because that has been taken into account within the design of the barrier itself. Okay, let's see another question here with differences between IA, IB, and IC. What advantages emerge from this protection concept? Let's see.
Yeah, so IA is suitable for zone 0, IB is 1 and 2, and IC is zone 2. So this has to deal with the redundancy of an intrinsically safe associated apparatus. So with regards to IA, the slide that we showed very early on, if you noticed, we had 3 Zener diodes. So that was our redundancy, right? So the difference between an IA barrier and an IB barrier, instead of having 3 Zener diodes, we would only have 2 Zener diodes, right? So most of the barriers that you will find, most of the associated apparatus that you'll find on the marketplace are generally going to be suitable for IA applications, which means that they can be used for zone 0. So there's not a huge cost differential between an IA product and an IB product. But you're basically, that's what you're doing. Is that
Well, actually, Bob, let me mention, since the question earlier on the voltage drop remind me of something.
Yeah.
There is another difference. If you want to go to an IB device, beside the diode difference, you can use a Zener, a resistor. I don't remember the type of resistor, but there's a specific resistor that must be used to limit current in IA circuit. So a resistor is a mandatory requirement, but on an IB, you can use different method of limiting current, which sometimes allow to have more power in the field. So in some application, you find power supply specific for when you require high power in the field, maybe a radar or some kind of device that require high current, maybe 100, 200, 300 milliamps. You might find an advantage using an IB type barrier, which cannot be used in zone 0, but allows for more power. But there are not many of those in the market. They're typically specifically designed for, like custom design for specific apparatus. Do we still have a few more minutes? Let's give it a few more minutes. We are 10 minutes past the hour. Can I install an I.S. barrier in the field or in a remote location? I can answer yes, because we do many times, but
so yes, you can. You can install them if it need. So for example, using that scenario with the 179 meters, if we found that we were 200 meters away and we needed to somehow figure out a way to solve this, well, barriers generally, the GMI product is actually rated for zone 2. So they can be actually installed in zone 2. But if we had to say, put them into a zone 1 area, then we can install the barriers into, say, either a flame-proof product, or we could do purging and pressurizing. So we can certainly take barriers and put them in hazardous locations if need be.
All right, let's try to move a little further. In which application can I use I.S.? Can I.S. be used? We discussed this during the presentation. Basically, all low voltage or low power applications, such as you can see listed here from, AI, AOs, voltage free contact, sounder beacons, but low power. If you need more power, you need to go to EXD, EXP, or EXM. There are different other methods of protection. And they're used in many industries. Basically, most industries around the globe have some kind of hazardous location. Some a lot, like in oil and gas, but some also small, but in food and beverage, for example, cacao powder, we serve Ferrero, Ferrero is, known around the world for Nutella, and they are made here in Italy, and they have hazardous location because cacao powder in itself can be dangerous. Okay, let's see. Well, what we are interested in webinars on, we get this question all the time. We want to know about functional safety. We want to know about safety relay. We have many webinars that we run. You look up our schedule, live schedule on our website, or you can look at the past webinars on our YouTube channels. This brings us to, I believe, the end of our question and answer section and we would like to hear from you in a different way. Let us know how we do it. Let me see if I can launch this poll. Launch the poll. Okay, so, well, we spent some time preparing these webinars. Bob, spends a lot of time preparing the webinars. He wakes up early in the morning to talk to you guys. Sometime late in the evening, depending on the time. He drinks a lot of coffee to be with us. So it's always a pleasure to let him know how he did. All right, guys, we have, you're still answering. After this, as I said, you look up our website, and we have a special section for training and webinars, and you can see what we're doing next. There's also other teams that run webinars. We have Mauro and Tino on functional safety. We have Andrea and Massimo on products. So, okay, let's end the poll here. And thanks for your answer. Excellent and good. Thank you very much.
Yes, thank you. Thank you, everybody.
And let me again take a moment to thank Bob. Let me share our contact again so you have those in case you need to contact us. We will share the slides at the end of the presentation to all the registered participants. So again, Bob, thank you very much. Thank you for your knowledge and thank you for the presentation.
Have a great day.
Have a great day, guys. See you soon. Bye-bye.
Ciao.
Ciao. And here we go.